Now, students, let's talk about half-life. And what this half-life states is that we have the half-life of these radioactive elements, and it is this half-life which is exploited to calculate the age of the substances, to the age of the bones, and what is generally called as dating, uh, and all that. So here we are just looking for the inclusive treatment of this half-life, how to calculate it. So if I have to define half-life, it is the time during which the nuclei, the half of the nuclei, suppose I have a sample with nuclei, and the time taken by this sample to have half of its nuclei decayed or disintegrated into their daughter nuclei, and this thing is called as half-life. And how to calculate this half-life of any radioactive material? We will assume that we have n0 radionuclei present in a radioactive substance at any instant, and then after time, say after time t half, what will happen to this n naught? It will become n naught by 2, and radioactive nuclei disintegrates, and we have this n naught by 2 radioactive nuclei which remains undecayed. Now after the time, if I go with 2 times t half, what will happen in this case? We will have n naught by 2 by 2 uh, radioactive nuclei which will remain undecayed. So it will be n naught by 4. And after 3 times t half, we will have n naught by 8 undecayed radioactive nucleuses. So we can illustrate this thing in terms of some canonical boxes. We have full sample, then we have half of it are filled, and then we have half of this portion, and this will go on decreasing. Okay, so if I assume that this is giving me the number n, and n0 is the total number of undecayed nucleuses. Now, what we know is that we have a relation. What we have, n is equal to n naught e to the power of minus lambda t. Right? So at t equal to t half, what will happen to n? This n will be simply n naught by 2. And what can we do after this is, so what we'll get is, we'll get n naught by 2 is equal to n naught e to the power of minus lambda t. So this n naught and n naught can be cancelled. I will have 1 by 2 equal to e to the power of minus lambda t half, because this condition goes with t is equal to t half. All right. Now, if I take log on both sides, I'll get 1 by 2 equals minus lambda t half. And what we'll have here is, we will have log 1 minus log 2 equals minus lambda t half. And that means we will have minus log 2 equals minus lambda t half. And that means I will have t half equal to log 2 divided by lambda to the base e. And when we convert this log of 2 to the base e, what we get is 0.693 3.1 by lambda. So what I get here is the half-life of substance having radioactive elements in it, and that is 0.6931 by lambda, where this lambda is already defined, and we call this thing as distinguishing constant. Now, so what does it mean here is that at this stage I will have N0 by 2 undecayed nucleuses. Then at the next stage I will have N0 by 8, sorry, N0 by 4. Then accordingly it will go N0 by 8, and so on and so forth. So I can have a graph that will go like this, and this graph, so this will correspond to my t half. Okay, uh, this will correspond to 2t half, and so on and so forth. This is how the graph will go. And this graph is going to meet at infinity, because we will have infinite number of atoms in that sample, which is undecayed. So what we have achieved is we have achieved the expression for half-life of a radioactive substance. So we can see that this half-life is inversely proportional to this to the distinguishing constant. And this half-life is giving us the measure. It's giving us the measure of time, basically. It's giving us measure of time. And it gives us the measure of time for which a radionuclide lasts one half of its initial numbers. And if lambda of the radioactive substance is large, suppose if this lambda is large, the half-life will be small. That's clear from the equation. So for large distinguishing constant, the half-life is going to be small. It means that the radioactive substance is having small half-lives will disintegrate very rapidly. And there we can take some examples. Suppose uranium. If I take uranium 238 and 92, its half-life is it's 4.50 times 10 to the power of 9 years. And if I take radium, with atomic number 88 and mass number 226, the half-life for radium is it's nearly 1620 years. And if we take radon, for example, radon with mass number 222 and atomic number 86, its half-life is 3.82 days. So we have elements whose half-lives are practically infinite, and we have elements of whose half-lives are small. And if we have to calculate the number of undecayed atoms in a particular sample, number of undecayed elements for n half-lives. For n half-lives. In that case, this n will be n naught times 1 by 2 raised power n. And that means this n by n naught will be 1 by 2 times 1 by 2 raised power n. And for t is equal to n times t half, what will be n? N will be t by t half. So what can we obtained from here is number of undecayed nucleases. That will be n naught times 1 by 2. I should have brought it here. Raised power t by t half. So this equation is going to give us the number of undecayed atoms in a radioactive substance after n half-lives. N half-lives. Okay, after n half-lives. Now, what is so interesting here is that we have some radioactive elements known as tritium, and plutonium. They have very small half-lives, very small. And these elements have decayed long ago, and hence these elements no longer exist in nature. However, we can have these elements produced artificially by means of nuclear reactions. So what we conclude here is that half-life of radioactive substances can be determined from rate of disintegration of the substance, lambda, and also the half-life of the radioactive substances is not affected by the change of temperature and pressure. And if we take a simple example at this point of time, like suppose I have some element, it has half-life, equal to 5 days, and and I want to calculate that what will be the number of what will be the time taken by 7 by 8th part of sample to decay, right? So how long it's 7 by 8th part of the sample is going to decay. So for this, what I have t half is 5 days. That's clear. Okay, then I can have n, and that n will be 1 minus 7 by 8 of n naught. That should be clear. So this will give me 1 by 8 n naught. So I'm able to get n by n naught equal to 1 by 8. Right? And I can use the formula that I had. That's n by n naught is equal to 1 by 2 raised power t by t half. That's the case, right? So, but this n by n naught, I have calculated this as 1 by 8. So I can write 1 by 8 is equal to 1 by 2 raised power t by t half is, it is given as 5 days, so I will write 5 here. So instead of 8 here, I can write 2 raised power 3. So what does that mean? That means t by 5 is equal to 3. So what does that mean? T is equal to 15 days. So the 7 by 8th part of the sample will decay in 15 days.